In this video, we are going to go over the solutions of some practice problems that augment Practice Quiz 5, just so that you have some extra problems to work out. And they also augment some problems we already reviewed this week, in particular practice problems 2G, number 13, number 18, number 20, and 2H, number 8. So if you don't remember these problems, you can go back to the lecture from Wednesday. November 6th. Okay, here's the list of the problems we're going to cover. The notes, this sheet of paper, these notes are on our D2L webpage. So 3B, 4, 9, 3C, 11, 13, 15, 3D, 5, 8, 9, 10, 3E, 8, 10, 3F, 6, 3G, 2, equilibrium number 2, part A, rotational dynamics number 11. I've tried to pick problems that are sort of not too difficult, but show sort of concepts, maybe help you get a feeling for the level of problems you should be able to manage. The main reason for this is Practice Quiz 5. There were a couple problems that were a little difficult, but they did cover concepts that were extremely important. However, you may have difficulty learning concepts with some of the harder problems, so I try to supplement some of these problems here. Okay, so let's get started. First problem is 3B number 4. That's this problem. A man lifts one end of a wheelbarrow with a vertical force F and holds it stationary. The horizontal distances from where he holds the handle to the center of mass of the wheelbarrow and to the point where the wheel touches the ground are shown in the figure below. So here's where the wheel touches the ground. If the mass of the wheelbarrow is 70 kilograms, what is the magnitude of the force F, this force F? Okay, so first step, when we have an extended body, we have to find its center of mass. Okay, we're not doing any supplementals. We're not doing any calculations of how you get the center of mass, but we did a bunch of these problems on Wednesday. These problems here in practice problems 2G. So you can take a look at that if you don't remember those. Okay, but they've located the center of mass here. What you do is you take the weight of the wheelbarrow and then you attach it to the center of mass, and you have this force going straight down. Okay, that's where the weight vector goes, at the center of mass of this body. Okay, then we have this force F going straight up. Then we have some contact force, some normal force of the ground pushing up on the wheelbarrow pointing in this direction. But the trick is where you can figure out that the wheelbarrow is pivoting around the wheel here. Okay, so this is the rotation point right here. Now, the idea is to calculate the torque about this rotation point. And if we calculate the torque about this rotation point, because this force is going straight through the center of the wheel here, the torque due to F1 will be equal to 0. Right? It doesn't actually matter whether you're calculating the torque at the center of the wheel or at the point of contact. Either way, you end up with F1. The force of the normal force will go straight through that point, and so therefore the torque will be equal to 0. Okay. Now, what we're going to do is we're going to say that the torque about the rotation point is going to be, the net torque about the rotation point needs to be equal to 0. Net torque is equal to 0 because it's in static equilibrium. So let's first get the torque due to the force F. Okay. Force F, the easiest way to do this because it's a vertical force is to draw a straight line through the force. You do that. And then the distance between the rotation point and that straight line going perpendicular is what we call R perpendicular. And that distance is 1.2. So we have the force times the R perpendicular, 1.2. So the torque is going to be F times 1.2. Because it's trying to make it go like this, it's trying to flip the wheelbarrow over like that, which is clockwise. Okay, so it's clockwise for that one. Now the weight of the wheelbarrow, as I said, is attached to the center of mass. So that force will be M times G, 70 times 9.8. but because it's a vertical force, the easiest way to calculate the torque is to draw a line through the force and calculate the R perpendicular going from the rotation point to the line, making a perpendicular angle. And that distance is not given, but you can figure it out because this is 0.9, this is 1.2, this remainder distance is 0.3 meters. Okay, so this R perpendicular here will be 0.3, and the force is 70 times 9.8. And that comes out to 2,006 newtons. And so I said the net torque is 0, so this guy is going this way. It's a torque this way, which is counterclockwise. So the sum of the clockwise must equal the sum of the counterclockwise torques. So F times 1.2 is equal to 206. So F is equal to 206 divided by 1.2. That comes out to 172. Okay, let's go on. Number 9, 3B. Okay, a 35 kilogram child rides on a merry-go-round that has a moment of inertia of 2,700 kilogram meters squared. When the child is located at an initial radius of 3.5 meters, the merry-go-round has a rotational speed of 1.3 radians per second. The child then moves to a radius of 2 meters, moves inwards, and the rotational speed of the merry-go-round changes. The question is, what is the angular speed of the merry-go-round after the child moves to a radius of 2.0? Okay, so the child and the merry-go-round are stuck together in the beginning. They rotate with the same angular speed. Then the child decides to move into a different radius. They still are stuck together and they rotate with some other angular speed. So this is a conservation of angular momentum problem. We need to calculate the moment of inertia of the merry-go-round plus the child initially, and then the moment of inertia of the merry-go-round plus the child in the final case. And then we'll have initial angular momentum equals the final angular momentum. Okay, conservation of angular momentum. Li, L initial equals L final. And the angular momentum initial is the initial moment of inertia, I initial, times the initial angular speed. They tell us that the angular speed is 1.3 radians per second. To get the moment of inertia of the merry-go-round plus the child is at a distance of 3.5 meters, and the child has a mass of 35 kilograms. So the moment of inertia of the merry-go-round is 2,700 plus the moment of inertia of the child around this rotation point, or the rotation axis. So that's mr squared. That's the 35 times 3.5 squared. So you add these together. This is 3,129 kilogram meters squared for the initial moment of inertia. So now we can calculate the initial angular momentum, I initial times omega initial. That's 3,129 times 1.3. That's 4,067. And the units, if you're wondering, is kilogram meters squared divided by seconds. Okay, now for the final angular momentum, that's the final moment of inertia times the final angular speed. Okay, for the final angular moment of inertia, now the child has moved into a distance of 2.0 meters. It still has a mass of 35 kilograms. So the total moment of inertia of the merry-go-round plus the child is 2,700 plus mr squared for the final r. So we have 35 times 2.0 squared. That comes out to 2,840 kilogram meters squared per second. Okay, so now the final moment, the final angular momentum is the final moment of inertia times the final angular speed. So that's 2,840 times omega f, which we don't know. We don't know the angular speed finally. So now we say this, which is the final angular momentum, must equal the initial angular momentum. And so we get the 2,840 omega f is equal to 4,067. And so omega f is equal to 1.43 radians per second. Okay, let's go on. The next problem is 3C, number 11. Okay, A student sits on a stool that is free to rotate. Initially, the student and the stool are motionless, and the student holds a bicycle wheel that is rotating clockwise. Okay, so it's going around clockwise. The student then flips the bicycle wheel upside down so that it is rotating counterclockwise. What happens to the student's motion after flipping the bicycle wheel? Note all rotation directions are as viewed from above. Okay, so the initial angular momentum is in the clockwise direction. That's because the student is not rotating, the stool is not rotating, the total angular momentum will be clockwise. So the final total angular momentum needs to be clockwise. If the total angular momentum for the final case is clockwise, and the wheel has flipped so that's counterclockwise, that means the student and the stool have to be rotating clockwise. Okay, so the student rotates clockwise because the total final angular momentum needs to be clockwise. The wheel is no longer clockwise; it's counterclockwise. So the student must be clockwise, and the total sum must also be clockwise for the angular momentum. Okay, let's go on to number 13. There's a large carousel in Pullen Park. This is a park in the city of Raleigh, North Carolina. When it is turned on, its angular speed increases with a constant acceleration until it reaches a maximum running speed of 0.53 radians per second in 15 seconds. Okay, question is, if a child is riding the carousel at a distance of 5 meters from the center of the carousel, what is her tangential speed when the carousel is at full speed? Okay, this is just a simple application of V is equal to omega r. So this should be something formula that's very familiar. V is equal to omega times r. The linear speed is equal to the angular speed, or you can say velocity. The linear velocity is equal to angular velocity times capital R, the radius. So 0.53 is the angular speed, and the radius is 5 meters. So multiply them together, you get 2.65 meters per second. Next problem is 3C number 15. Okay. A solid sphere of radius 7 centimeters and mass 0.2 kilograms starts from rest and rolls without slipping down a ramp. After the sphere has dropped a vertical distance of 0.3 meters, what is its translational speed? How fast is the center moving? Air resistance and velocity of friction may be neglected. Okay, so this is a conservation of energy problem, but we have to also take into account the kinetic energy of rolling, so the total kinetic energy, which includes rotation and translations. Okay, so we have conservation of energy, that's this guy here, Kf plus Uf is equal to Ki plus Ui, but let's take into account all the little pieces of the kinetic energy. Also, the kinetic energy is 0 because it's starting from S. The initial potential energy, let's say that it's starting from a height that's given here, say it's 0.3 is initial, and then it drops down to 0. Y final will be 0. So mgy initial is 0.2 times 9.8 times 0.3 for the potential energy. That's 0.588. Now, here's where the rotational kinetic energy comes in. The kinetic energy is the translational kinetic energy plus the rotational kinetic energy. So this is this formula that we have 1/2 mv squared. Let me draw this out a little bit better. mv final squared plus 1/2 r omega final squared. Okay. Now for a solid sphere, this is I is 2/5 m r squared. Okay. So I put that in there, and then we also use this fact that omega final is equal to V final divided by R, okay? And so we will end up getting, let me plug this in, you get 1/2, 2/5 mr squared times V final squared divided by R final, or R squared. And so these will cancel. Okay. And then we have 1/5. Sorry, get this out of the way. Then we get 1/5 mr squared here. Okay. Times well, r squared divided by r squared, so these cancel times v final squared. Sorry about that. So I get 1/5. That's what I have here. This becomes 1/5 mv final squared. Okay. So now we need to add the 1/2 plus the 1/5. Okay. And so if you do that, we get that k final ends up being 0.7 mv final squared, or then plugging in that m is equal to 0.2, we end up getting 0.14 v final squared. Okay. Now, so now we're set up to say k final plus u final is equal to k initial plus u initial. So this was k final. There was u final was 0, so we have 0.14 v final squared is equal to the k initial 0, u initial is 0.588. So we have v final squared is equal to 0.588 divided by 0.14. You get v final as the square root of that, so it's 2.05. All right, so this is a little bit messy. Let me just review the key concepts. So one key concept is the total. Kinetic energy is including the translation kinetic energy plus the rotational kinetic energy. And then we use the fact that the moment inertia is 2/5 mr squared for the sphere, and then omega is v over r for the angular speed is equal to linear speed over r. And so then I can write this guy as 1/2 times 2/5 times mr squared times v squared divided by r squared, so the r squareds cancel. Then we get 1/5 mv squared. So then we get 1/2 plus 1/5, that would be 5/10 plus 2/10. That's equal to 7/10 mv squared. 7/10 mv squared. And so now what we do is we say, okay, k initial plus u initial is equal to k final plus u final. And so k initial is 0, u final is 0, the height is 0. And then this guy was mgy initial. And then this guy is 7/10 mv final squared. And so now we solve for v final and we plug in the numbers. Okay, so that's how this works. It should have been a lowercase m. All right, let's go on to the next problem. The next problem is 3D number 5. Okay, when an ice skater spins on the ice with her arms outstretched, she has a moment of inertia of 4.6 kilogram meter squared and angular speed of 3.2 radians per second. When she brings her arms in, tight against her body, her moment of inertia becomes 2.7 kilogram meters squared. What is her new angular speed in this position? Okay, it's conservation of angular momentum. The initial angular momentum is I initial times omega initial. I times omega. That's 4.6 times 3.2, that comes out to 14.7. The final angular momentum is I final times omega final. That's 2.7 for the final moment of inertia times the final rotational speed, angular speed or angular velocity. So omega final is going to be, so this guy equals this guy. So omega final is 14.7 divided by 2.7. That's 5.45 radians per second. The next problem we cover is number 8 on 3D. Okay. A uniform 105 kilogram beam with length 55.6 meters is supported by a vertical, that should be vertical with a C, vertical rope right here, this rope here, located at D equals 1.3 from its left end. So here's the left end of the beam. So this distance is 1.3. The right end of the beam is supported by a vertical column right here. Okay. Find the tension in the rope. So how much is the tension? Okay, the first step is we have this uniform beam, and we put the weight of the beam at the middle of the beam, where the center of mass is, the weight is 105 is the mass times g, 9.8 is 1029. It goes straight down from the middle here. What we're going to do now is so we can choose, so this is an equilibrium, and so we're going to calculate that the net torque about some point is equal to 0. We're going to choose the rotation point to be here, because by choosing it to be here, the force that the support is exerting on this beam is going to not make any torque. That's the key step here. Okay, so we're going to calculate the torque about this point. That will remove this force from the torque calculation. So now we calculate the torque due to this tension. So it's making 90-degree angle with the lever arm vector. So we just do 4.3. Okay, so this distance times t. So we need to figure out what this distance is. The full length of the beam is 5.6 meters. Full length. Okay, so this section is 1.3. So then if we do 5.6 minus 1.3 is equal to 4.3 meters. And so that will be this distance here. Okay. So we have 4.3 times t. Then for the torque due to the weight, that goes directly down from the middle of the board, the beam. And so this distance is half of 5.6, that's 2.8. So we have this distance, 2.8 times the weight, which is 1,029 newtons, and we get 2,881. So the clockwise torque of this string and the counterclockwise torque of this weight, they must cancel. So the 2,881 must be equal to 4.3 times t. So t is 2,881 divided by 4.3, which is 670 newtons. Let's go on. Now we have number 9. Number 9. A 13-Newton basket of apples sits in the very middle of a 2.0 massless beam attached to a wall and held in place by a cable at 35 newtons, 35 degrees as shown. What is the tension in the cable in newtons? Okay, so this is the place where it's rotating, where it pivots, there's a hinge. So that's where we're going to choose the rotation point, rotation axis. We have the weight of the basket of apples, 13 newtons going down. We have the tension of the string going at this 35-degree angle. Okay, and then but in this case we say the beam is massless, so we just have the weight of this the apple basket and the string tension. Okay, so here let's do first of all the weight of the apples. It's at a distance. Okay, so we're going to draw a line through the apples like this. And it's going to make an r perpendicular distance, this distance from here to the line that contains this weight force. And so that distance will be, the apples are in the middle, so it's going to be at a distance of 1 meter. So we have 1 meter times the weight, which is 13 newtons. So it's 13 newtons, and it's going to try to rotate this way, which is clockwise. Now then we have this tension here, and so we have the angle between the lever arm vector, which is going in this direction, and this guy, so it's 180 minus 35. Note, 35 is not the angle. This is the r vector, and if you want to get the angle between the r vector and the force, you want to think of drawing the r vector from the same beginning point as the force. Okay, and then this angle is going to be 180 minus 35, which is 145. All right, now having said all that, it ends up that you actually end up getting the same answer once you take the sine of 145. In other words, if you use the wrong angle, you would have ended up with the same answer anyways. So it doesn't really matter that much. Okay, now the torque due to this tension will be then the lever arm distance, which is 2.0, times the magnitude of the tension, which is t, times the sine of the angle, 145. So you get 1.147 times t, and it's trying to rotate it in this direction, which is counterclockwise. So we are in equilibrium, so the 13 must balance out the 1.147 t. So t is 13 divided by 1.147, and so t is 11.33 newtons. Okay, let's go on to the next problem. So this is actually kind of similar to what problem we just did. Solid sphere of radius r is equal to 7 centimeters and mass m equals to 0.2 kilogram. Starts from rest and rolls without slipping down a ramp. after the sphere has dropped a vertical distance of 0.3 meters, what is its translational speed? How fast is the center of mass going, essentially? If the moment of inertia in the solid sphere is 2/5 mr squared, and then neglect air resistance and losses due to friction. Okay, so it's conservation of energy, but the kinetic energy, again, has translational and rotational. Once again, we said omega is v over r. Then we can write 1/2 mv squared plus 1/2 I times v squared over r squared. Then plug in I is equal to 2/5 mr squared. Put that in here. We have 1/2 2/5 mr squared over r squared. We did exactly this before. Times v squared. So we have 1/2 mv squared. These numbers should look familiar. Plus 1/2 mv squared. That's what we just did. And so that comes out to 7/10 mv squared. If you're not believing that that's what we got before, here's the work we had before. Okay. And so that comes out to, now then we put in the mass, 0.2. So we end up with okay, now I'm realizing this is actually an exact repeat of the same question. So we don't need to do this. It's exactly the same. My apologies. It was sometimes they repeat problems from previous years, so I didn't realize they're identically the same. Just a slight difference in the inclusion of the moment of inertia here. Okay, so let's skip that. We've already done this. Let's go on to 3E, number 8. Okay, a student sits on a rotating stool holding a 5 kilogram mass in each hand. When his arms are extended horizontally, the masses are 0.9 from the axis of rotation, and he rotates with an angular speed of 0.8 radians per second. If the student then pulls in the two masses horizontally to 0.4 meters from the rotation axis, what is his new angular speed? The moment of inertia of the student and stool combined without the two masses is a constant 4.2 kilogram meters squared. Treat the masses as point masses. Okay? So this is angular momentum conservation. Right. So this says 0.9 squared. There's a squared hiding under the staple. Okay, the initial moment of inertia is 4.2. That's given for the student plus stool, plus the moment of inertia of the masses. One mass will be m and r squared. The distance is 0.9. Then we have another one for the other, 5 times 0.9 squared. The sum comes up to 12.3. For the final moment of inertia is 4.2 again, but now the distances are 0.4, so we have m 0.4 squared, m, which is 5 times 0.4 squared, that's a 4.4 squared, that comes out to 5.8. So initial angular momentum is equal to initial moment of inertia times initial angular speed. So we have 12.3 times the initial angular speed, which is 0.8, that's given, is equal to 9.84. Now for the final angular momentum is the final moment of inertia times the final angular speed. So that's 5.8 for the final angular moment of inertia times omega final, which we don't know. But then L final must, this guy must equal to this guy, or this guy must be equal to this guy. Okay, so we have 5.8 times omega final is equal to 9.84. So we have omega final is 1.7 radians per second. All right, now let's go on to number 10. Okay, a meter stick is free to rotate without friction around its center of mass if an 8 Newton weight is hung 0.4 from the center of mass. Okay, so here's the rotation axis, the center of mass. The question is, how far from the center of mass should a weight of 21 newtons be hung toward the other end? Okay, so that the meter stick is balanced. So they want this distance here. Okay, so let's call this distance x. So we want the net torque to be 0. Okay, the rotation axis is right in the middle, so the weight of the ruler stick would be piercing through the center of mass, through this rotation point, and so as a result, it doesn't produce any torque, so the weight of the meter stick doesn't matter. But now we get from the 8 Newton Newton weight, we get a clockwise torque, and so the distance is 0.4 times the weight, which is 8, the force 8, 3.2 clockwise. Now then we have this weight here going counterclockwise, so this lever arm distance is x. The weight is 21 newtons, so we have x times 21. So the clockwise total must equal the counterclockwise total for the net torque to be 0, and so x must be equal to 3.2 divided by 21, which is 0.15 meters. Let's go on. Next problem is 3F number 6. Okay. So now a person tightens the nut with a wrench as shown in the figure. The wrench handle is 30 degrees above the horizontal, and the person applies a force of 0.5 meters from the center of the nut. If the applied force is 15 newtons straight down, what is the magnitude of the torque that is applied by this force? Okay, so we have the force here. We have this is the rotation point. We have this lever arm vector here. So we want, so I'm going to draw it in here. So this angle is going to be equal to, well, you have to do a little geometry here. So this is 30 degrees. This is 60 degrees in this right triangle. And this will be equal to 120 degrees because it's 180 minus 60. So tau is equal to r times f times the sine of the angle between. The angle between is 120. The r is equal to 0.15, this distance. The force is 15, so 0.15 times 15 times sine of 120 becomes 1.9 Newton meters. Okay. Now, of these supplemental problems, we actually didn't do it. None of these supplemental problems have Newton's second law for rotations, but if you were, suppose, let's make an extension to this problem. Suppose now let's approximate the wrench as some object, maybe let's just do this. Let's extend this problem. So now we have the wrench as a rod, okay, and at the moment of inertia for the rod rotated about its end is 1/3 ml squared. Okay, so let's say we have this length 0.15 meters, and so we are told that the torque from this problem is 1.9 Newton meters, and let's say that the mass of this wrench is equal to 1 kilogram. Just make some nice numbers. And suppose we want to know what is the angular acceleration of this wrench due to this net torque. Okay, let's suppose it just you exert this torque and let it accelerate, do an angular acceleration. Then what you'd have is tau net is equal to I times alpha. So alpha is equal to net torque divided by I, right? So we have 1/3 ml squared, and net torque is 1.9. So 1.9 divided by 1/3 times 1 times 0.15 squared. And so we'll add our calculator. And so we get 253 radians per second squared. Okay. All right, that's about it I wanted to do for that problem. So now let's go on. The next problem is 3G number 2. Okay, another equilibrium problem. A uniform wooden board has a total length of 5 meters. The board is balanced horizontally at a point which is 3 meters from the left end of the board, while a block with mass m sits centered on the far right end of the board as shown. If the system is in equilibrium, the mass of the wooden board must equal what? Okay, so we have this board with unknown mass. but it's uniform, so its weight goes from the center of mass right in the middle here. So we draw mg going straight down here. Because the length of the board is 5, then 5 divided by 2 is 2.5, so this distance is 2.5. So then this is my rotation point. It's balanced right here in the middle. And so, not in the middle, sorry, scratch that. It's balanced right here at a distance 3 from the end. So that means this little piece, this little distance here is going to be 3.0 minus 2.5, which is 0.5 meters. Okay. And now for this distance from here to there is 2 meters. That's because this is 3, the whole thing is 5, so this is 2 meters. Okay, this sort of distance subtraction thing you have to get used to when you're doing these kinds of problems. So then we have a torque due to this mass going in this direction, rotating like this. That's clockwise, so it's the weight, which is m times g, times the lever arm distance, which is 2.0. That's 19.6 times m. Then we have the torque due to this weight of the board, so that is going counterclockwise. So that's, let's call it small m times g times this lever arm distance, which is 0.5. So that becomes 4.9 times small m. So now small m is the weight of the board. This guy must equal this guy to balance off the torques. The clockwise must balance off the counterclockwise to get net torque equals to 0. And so small m is equal to 19.6 big M divided by 4.9, which is 4 times big M. Okay. Let's go on. Next problem is the first part of 2a. Okay. Sorry, the first part of 2, which is part A. The uniform rod of length 2.5 meters and mass 3.5 kilograms. The rod is pivoted from a wall as shown, and the angle theta between the rod and the wall is 45 degrees. A horizontal string is attached to the free end of the rod. The question is, what is the tension in the string? Okay, so we have a pivot here. So we have some unknown forces coming from the pivot. Okay, so we have some parallel to the wall, some perpendicular to the wall. Don't worry about that because we're going to calculate the torque about this pivot point. This will be a rotation axis, so the torque due to these forces will be 0. Okay, first let's get the torque due to this tension T. Because it's a horizontal vector, the easiest way to calculate is to do the R perpendicular. You draw a straight line like this, and then draw a straight line. We can figure out what this R perpendicular is. All right, this angle is 40, sorry, it's this angle I actually want. It is 45 degrees, okay? And so this is the adjacent side, so it would be, this distance is 2.5, that's the length of the hypotenuse. This is this side of the right triangle, so 2.5 times the cosine of 45, that's 1.77 meters. So it's R perpendicular times the force T, so 1.77 times T. Then we're going to get the torque due to the weight, here. So we draw this line through the vertical vector. So we just draw this vertical line, okay? And so we can calculate this R perpendicular here. And again, what we'll have, so I'm actually taking this angle this time. That's 45 degrees. I have a little triangle, okay? And so the length of this triangle here, this hypotenuse here, is 2.5 divided by 2. It's half, because this guy isn't on. I forgot to say this explicitly. Just to remind you, the weight goes from the center of mass, starts from the center of mass, and pulls it down. Okay, so that's why it's halfway along the rod. Okay, so that's why this guy is 2.5 divided by 2. And so then this guy would be the adjacent to, would be the opposite to this angle. I don't know if I did adjacent for this guy and then did opposite for this guy. I just kind of chose them randomly. So it's 2.5 divided by 2 is the hypotenuse times the sine of 45, this angle here. And that comes out to 0.884. That's, this side would be 0.884 meters. Okay, but now to get the torque, that will be the weight of the rod, so 3.5 kilograms times G, 9.8, times the R perpendicular for that guy, okay? So that's my R per beta for the rod. And so that comes up to 30.3 Newton meters. So the net torque is equal to 0. So this is going to give you this T gives you a counterclockwise torque, whereas the weight gives you a clockwise torque. They will balance each other out to give net torque equal to 0. So then you get T, the tension, is equal to 30.3 divided by 1.77. And so the torque, the tension is 17.1 newtons. All right, this was a bit of a complicated problem, actually. Okay, let's go on. The last problem we'll do is rotational dynamics, number 11. So a particle of mass 2.0 kilograms is moving with velocity 1.5 meters per second I plus negative 2.5 meters per second J at the point negative 2.0 meters I plus 2.0 meters J. Find the angular momentum of the particle relative to the origin. Okay, so this is angular momentum R cross P, or because P is equal to M times V, you can write it as R cross M times V, or you can pull the M out outside. So the M times R cross V. So let's just do R cross V and multiply the M's at the end. I find that faster. Okay, now I'm going to write down the components of R. R is negative 2, 2, 0. That was given in the problem. The components of V is 1.5, negative 2.5, and 0. The Z components in each case are 0. Okay, so for the X component, you cross off the X column, and you take the product of these diagonals, going downwards to the right, 2 times 0, and then subtract off 0 times negative 2.5, everything is equal to 0. For the Y component, you cross off the middle, then you cycle this first column to the end here, and then you take the product of the diagonals, that's 0, minus the product of the off diagonals, which is also 0. Now finally you cross off the Z column, and you take the product of the diagonals, that's negative 2.0 times negative 2.5, okay, minus the product of the off diagonals, 2.0 times 1.5, that comes out to 2.0. So that means we have 0, 0, 2.0. So R cross V is 2.0. The units are meters squared per second. And so that's k hat, because it was only the Z component. So the angular momentum, we have to multiply by this M. I remember I took that out here. So multiplying by M was equal to 2, so I get 4.0 times kilogram meters squared per second, k hat. All right, so I will, so if you're listening to this before Sunday, I will be announcing some special office hours on Sunday in the afternoon. Stay tuned for an email from me announcing the exact time.